Everyone's comfortable with this? Hopefully it's not very obstructive, right? Okay. So again, let me emphasize the key point here, right? So epsilon here indicates the difference between the generalization and training error, not just the absolute level of the generalization error. It's just the difference between the generalization and training error. You have to account for the training error in the advanced learning setting. And here, we can see that for the agnostic learning, the sample complexity bound also includes the size of hypothesis space. So that means the Occam's razor principle is justified again, right? So to achieve the same difference between the training error and the true error, if your hypothesis space is smaller, meaning that you choose a smaller, easier, less complex hypothesis space, the required number of training examples will be smaller. Right? That's why we should favor the Occam's razor principle. And also this delta determines the sample complexity bound as well. Right? If you want to increase the confidence level, you got to supplement more training examples. Okay. And further, if we can switch epsilon to m, right, meaning that, okay, we're going to fix number of training examples. And then we can get the so-called generalization error bound. This is the bound telling us how much the true error will deviate from the training error. So the bound is in this way. Right? This is very simple to derive that. Just switch epsilon to m. And now we can claim that suppose we are given m training examples, then with high probability, at least 1 minus delta, the generalization error is upper bounded by the training error plus this term. So actually, this is a probabilistic bound telling us what's the difference between the true error and the generalization and the training error. So we can
sort of a theory question. Is the reason we see the opposite of this when we start like letting our trees get super deep essentially because we're creating a huge hypothesis space, and that's making it so that even though training error goes down, generalization error starts to go up?
That's a good question. Yeah, you can view it that way. Like because in both cases, the learnability depends on the logarithm of the size of hypothesis space. That's very interesting. But just be aware of the difference between the two conclusions, right? The first conclusion tells us if m is bigger than this, then we can guarantee the learned hypothesis whose true error is strictly less than epsilon with high chance, right? But here, the second one, the conclusion is different. If m is bigger than this, then the true error, the difference between the true error and the training error is less than epsilon, not just the absolute level of the true error less than epsilon. So this is a key difference. But if you just look at the form of the sample complexity bound, it's really similar, right? And both sample complexity bounds dependent on the size, log size of the hypothesis space, which reflects the complexity or the expressiveness of your hypothesis space, right? But what is the problem here? Have we got a happy ending?
So the true error could be really huge, right? You don't know if this.
Yeah, definitely. But other than that, I mean, those are just estimates of the true error. But other than that, I mean, just in terms of the sample complexity bounds, what things can make you frustrated? Any thoughts?
Is it hard to know how far off you are?
Oh, how far we are is actually can be described by this generalization error bound, right? So as long as you can calculate the logarithm size capacity space. Yeah. But actually, the problem has been pointed out by you guys several before the topic. Okay. When we talk about consistent learning, that is here. We assume the hypothesis space is finite, right? So that you can calculate logarithm size hypothesis space, which is just a number, right? But what if your hypothesis space is infinite? Okay. So even for the simple linear classifiers, the hypothesis space is infinite. Why? Because all the feature weights and vast parameters, they're continuous. They're real value numbers, right? You have an infinite number of choices. In that case, the logarithm of size hypothesis space will be infinity, right? And then your sample complexity bound is actually nonsense. It's not meaningful at all, right? You will say, okay, if m is bigger than infinity, well, you can get whatever error level under whatever confidence level, right? Infinite elements. So this motivates the so-called Vatanen-Chervonenkis dimension, abbreviated as VC dimension. So VC dimension provides such a measure for both finite and infinite hypothesis spaces. And we can use VC dimension of a hypothesis space to describe or measure the capacity of that space, and use that to derive sample complexity bound and generalization error bound in both agnostic learning and consistent learning settings. Okay, so before we talk about the definition of the VC dimension, right? So I want to use a more concrete example to highlight why it's important in computational learning theory. Right? So we just use this like silly example. Right? So suppose we want to learn a rectangle classifier. Right? It's very simple classifier. This is our target function, the true concept. Right? So every point inside this rectangle classifier are positive, and outside are negative. Right? So we want to, given a set of training examples, we want to learn a rectangle classifier which to be as close to the ground truth rectangle classifier as possible. At the beginning, while you only have these three examples, while you learn rectangle classifier will be like that, we know that there's a huge gap between your learned classifier and the ground truth, right? And with the increase of the training examples, you can view that, okay, with more training examples, your learned classifier is getting closer to the ground truth rectangle, right? So you can expect that with more and more training examples that your learned rectangle classifier will get closer and closer to the ground truth classifier. And finally, I mean, in the end, we'll believe that your learned rectangle can be arbitrarily close to the ground truth rectangle. Okay? That's the intuition. But how do you show that? How do you estimate how many training examples would you need to achieve the epsilon difference between your learned rectangle and the ground truth rectangle? Right? Remember, this is the topic. This is the key question the computational learning theory wants to answer. Right? To answer this question, we need some measurement of the capacity or the expressiveness of your rectangle classifier hypothesis space. Okay. And hopefully this gives you enough motivation for the VC dimension. Right? We do need some finite measurement which can reflect the expressiveness or capacity of hypothesis space. Even the hypothesis space itself might contain infinite elements, infinite choices.
So when you say expressiveness, what does it exactly mean for the hypothesis?
So exactly means that, okay, what kind of, expressive means that what kind of, how flexible it can represent or classify complex cases. Like you have a 10 points, in whatever labels of these 10 points, can you always find a corresponding classifier in a hypothesis space to give correct prediction? Okay. So we're going to reach to this point right now. Any other question? Okay, that's a great question. So this dimension is defined on the concept of shattering. Shattering actually defines what you just mentioned, the expressiveness. So when we want to look at expressiveness or expressivity of lines, for example, right? Suppose our hypothesis spaces are just lines in the on the planes, right? So we want to just for a line experiment, right? We want to say if I use these lines to classify 2 points, right? How well can we do? Right? So suppose you are given 2 points, right? So you can consider all kinds of possible labelings on these 2 points. Actually, you have 4 possible labeling schemes, right? Positive, negative, 2 negative, negative, positive, and 2 positives, right? So we will see that, okay, for every possible labeling scheme, we can always find a corresponding line in our hypothesis space which correctly predict the labels. Right? So you can see that for 1 positive here, 1 negative here, you find a line here, well, you correctly predict both labels, right? If all points are labeled as negative, right, you just place a line here, you give correct predictions. And similarly, for the remaining labeling schemes, you can find a corresponding classifier which perfectly predicts the label, right? So from this simple experiment, we can see that it is possible to draw a line that separates positive and negative points in all labeling schemes, right? In this case, we are confident to say that, okay, our line hypothesis space are enough to shatter 2 points. Linear functions are expressive enough to shatter 2 points. Right? What about 14 points? Can our line classifiers expressive enough to shatter 14 points? Any thought?
Does it depend on how the points are labeled?
Yes, exactly, right? But when we say, okay, can shatter, that means that, okay, for every possible labeling scheme, you should be able to correctly predict those labels. That's quite strong requirement, right? That will be possible. Okay. So for this simple case, right? Okay, you put the left half points as positive, and the remaining half of the example is negative. Well, you can find a line which can perfectly separate them, meaning that they can correctly predict every label, right? But what if you mix the labels in this way, right?